really what a shock wave is an instantaneous change in pressure. And so that change in pressure propagates through the air, from the aircraft down to the ground, and our ears hear that, and that's what we perceive as sonic booms.
This is the crew brief for CISBoomDA Flight 1. The objectives for today is the real-time display of the sonic boom ground footprint in the rear cockpit of the F-18.
We have 7 different recorders out in the field that we'll be using, and we want to, to record sonic booms. And I'll be the one communicating with the control room, communicating with the rest of the project team as to the test points that we want to fly.
Ready. Mark, rolling.
Mark, please copy Mark.
Copy, Mark. Okay, repeat on the same one.
Repeat. That's affirmative, repeat.
So my role is riding in the back seat, and I have the tablet that displays where the boom is hitting the ground. I'm giving the pilot feedback on speed up, slow down, to sort of get the boom where we want it to be.
You want to get your flight path in the right place in space. The scientists, of course, want this as accurately as possible. We've got GPS receivers measuring things within at least 10 feet. We aren't going to hit 10 feet accuracy every time, except if we're lucky. But we get as many of the parameters as close as we can, and then the scientists can work the data out and see how we did, but more importantly, see how the algorithm did and see whether the display is working correctly.
1.3.
Copy, showing 1.3. Awesome, we're there.
This is the cockpit display for the Cockpit Interactive Sonic Boom Display Avionics, or CISBoomDA. Start to generate the impact area where the sonic booms hit on our ground. Over here we had a bunch of sensors on the lake bed to measure the effect of the sonic booms. And for the test, we were looking at how the real-time display predicts the sonic boom, where it hits, when it hits, and the intensity of the boom. That's shown by the colors. And we compare that to measurements on the ground. Oh, we got one. We got one.
Showing 4 miles past.
Test point complete. We did see ISO temps. We're good to proceed to the next run.
Copy that.
The next pass we're going to do what we call our low boom dive. I don't know if you're familiar with it, but the aircraft actually flies at about 49,000 feet subsonically, does a dive, an inverted dive till we reach supersonic speeds, and then recovers. That's our low boom dive. We use it a lot in our testing to simulate what a low boom demonstrator or a low boom aircraft might sound like.
Mark.
Copy Mark.
What PC Boom and CISBoomDA does to compute where the boom's going, the Mach number of the aircraft, you have a certain shaped Mach cone, kind of like a wake coming off a motorboat, a V-shaped wake, but in an aircraft it's a 3-dimensional cone.
Starting with Bravo, please report what you heard. So what we're trying to do is design aircraft that produce quieter sonic booms, or as we're calling them, low booms. If we're able to do that, hopefully we can get some of the regulations changed so that we can have sonic booms over land, but just a lot quieter sonic booms over land.